Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on your Zybooks section 14.2 titled Tree Application Examples. This is just scenarios where trees can be of use. Alright, so the first part of this section is on game trees. And they use like one of the simplest of games to demonstrate the use of trees, tic-tac-toe. Alright, so in 1997, a chess playing computer program called Deep Blue, developed by IBM, beat the reigning world champion of chess, Garry Kasparov, in a 6-round series with 2 wins, 1 loss, and 3 ties. It's not clear whether the victory showed that computers can reason as well as humans, as some claimed. The victory did establish, though, that computers are better at evaluating complex game trees, the basics of computer-based game strategies. A game tree shows all possible playing strategies of both players in a game. Each vertex in the tree represents a configuration of the game, as well as an indication of whose turn it is to play next. For chess, a configuration would be the location of all the pieces still left on the board. Here we're illustrating game trees in a much simpler context, right? The very simple game of tic-tac-toe. So the picture below shows the first 2 levels of the game tree of tic-tac-toe. Boards that are equivalent by a rotation or flip are not shown. So again, you start with a blank, tic-tac-toe board, and then X goes first. So they could put, upper left corner, the middle, upper middle. And again, they said the ones that are equivalent to a rotation or a flip, this is equivalent to flipping. That's why they don't have it in the upper right corner, because it's equivalent by symmetry to this one. They don't have one in the lower left corner because, again, it's equivalent by symmetry to this one. They don't have one in the lower right corner because it's equivalent by flipping, rotating to this one. But that's it, so that's why there's no 4 corners. This one here on the right, where there's X here, is equivalent to having X here, here, or here, right in the middles of the outside rows and columns. And this one in the middle is like the only one of its kind, really. Right. So you have, if you ignore all the boards that are equivalent due to symmetry, you'd have these 3 possible moves. And then from each move, you go to the, alright, it's O's turn. And then look at all O's possible moves. Right. And again, they ignore certain moves due to symmetry. Right. So having X in the upper left, O in the upper right, would be equivalent to having X in the lower left, O in the lower right. If you just flipped it, rotated it, or reflected it across the horizontal, across the middle row. So you're not seeing that board. Right. So again, and then same here. X is in the middle. The next move for O could be above it, which would be equivalent to putting it on any of the four middle pieces, or putting it in the lower right, which would be equivalent to putting it really in any of the corner pieces, and that takes care of those. And then X here, and again, they're showing you possible moves as you go down the tree, possible different configurations of the board. Now the root of the tree is the initial configuration of the game, right? That's an empty grid. The odd levels of the game represent choices of play for the X player. Right, so level 1 was for the X player. All these level 2 boards were for the O player, and so on. The even level represent choices of play for the O player. The children of a configuration C are all the configurations that can be reached from C by a single move of the correct player. So hopefully you remember section 14.1, right, all the definitions, because they're coming back here. So like here's the root board, and then these are its 3 children, And then this board has 5 children. This board has 2 children. This board has 5 children as well. And then you got parents, and remember ancestors, descendants, leaves, right? Leaves were those vertices that had no children, and so on. Right? There are lots of definitions in section 14.1. A configuration is a leaf vertex if the tree if the game is over. Right? So if you get 3 O's in a row, 3 X's in a row, either vertically, horizontally, or diagonally, if you get that vertex, that configuration, the game is over, and that particular configuration would have no children. You wouldn't move on, and that's called a leaf. So yeah, for tic-tac-toe, the game is over when one of the 2 players has won or the board is filled up. Right? If all 9 spaces are filled, then you have a tie game. Alright, so I'll play this animation for you. This animation below illustrates a portion of the tic-tac-toe game tree near the end of a game. So here's a subtree. Remember, a subtree takes a vertex and lists, and then takes you down through all its descendants. Right, so see the starting subtree rooted at this configuration here. So say X plays next. It could play here. That's one child. It could play here, another child, or it could play here, another child. Right. Then O plays. So starting here, O could play here or here. Now, if O plays there, the game is over. This will be a leaf. This won't have any more children. If O plays here, the game isn't over yet. You would continue on. Same here. Now it's O's turn. Now O could play here or here. Now if O plays there or there, O wins. And you got the 3 O's in a row either way. So both of these configurations, these vertices of the tree would be leaves. They wouldn't have, you wouldn't continue on. The game is over. And here, O could play here or here. Now if O plays here, the game's over. There's another leaf. If O plays here, the game continues. Right, and you can have that'll have more children, so they do that. All the ones where O wins, you don't keep going, but this one here, it's X's turn. X plays there, it's a tie. Here, X plays there, it's a tie. And there are your leaves, right, where the game ends. So there's 6 leaves up here. Okay. All right. So theoretically, a game tree can be systematically analyzed to determine optimal playing strategies for each player. However, in practice for most games, the corresponding game tree is much too large to build and analyze in its entirety. I mean, tic-tac-toe wouldn't be that bad. You could make a complete game tree for tic-tac-toe in a reasonable amount of time. All right, because there's not that many. There's less than 512 different game configurations, right? 2 to the 9th. And there's actually a lot less than that. Probably, I think there's less than 9 choose 5. Because remember, a tie game will have 5 O's and 4 X's, and that'll be equivalent to having 5 X's and 4 O's, right? You just switch the role of X's and O's. So 9 choose 5, 9 choose 4, right? Whatever that number is. There's going to be you don't really have to do that much checking with tic-tac-toe. But, chess, even, checkers, all sorts of games, the game tree would be incredibly large. Programs like Deep Blue build partial game trees starting from the current configuration in the game and estimate the best next move based on the results of the partial tree. Because again, a game tree for chess would be enormous, right? Because of all the different ways the pieces can move, and there's 64 squares on the board, 16 pieces on each side. I mean, it would be quite the undertaking to list an entire game tree for chess. Tic-tac-toe and chess are examples of deterministic games, whose outcome is completely determined by the choices made by each player. A game that involves rolling a pair of dice or shuffling a deck of cards introduces randomization into the game, right? So the player's choices don't always affect the outcome. Probability theory, as well as game trees, are required to analyze games with an element of chance, which I don't think we're going to get into here. Alright, so some activities, again, just based on tic-tac-toe, simple introduction here. Does the shown configuration have a child that is a leaf in the game tree? And they're telling you X plays next. So I'm going to draw this one up and show you what the next level would look like. Right? I know you could figure it out probably, but let me just show you real quick on paper. Alright, so here's the configuration they gave us, and what we're creating here is a subtree of the entire game tree, a subtree rooted where this is the root, this configuration. And they're saying, you know, X plays next. Right? X plays next. So there are 3 places that X could play. Right? So I'll make the 3 children. Three different configurations. Alright, so I'll just make the same configuration again for all 3 of these. And then we'll just add an X into one of the blank spaces. Alright. So again, X could play here in the upper left corner. And look, X wins. In that case, you got 3 in a row diagonally. So this is a leaf. So the answer is yes. You can have a leaf coming off as a child of this configuration. X could play here, and then this would continue. Right? Because again, nobody's winning yet. Then O would go. Alright, then O would go. And there's only 2 places O could put in. But, you know, and then I go O moves. Right, but I'm not going to draw those. And then X could play, you know, upper left corner there and here. And again, X wins in this scenario. So we have another leaf. Right. So the tree would not continue on from these 2, but it would continue on from here. And if O played here, then you'd have another ending of the game. If O played here, the game wouldn't be over, but then X would win. Right? But yeah, so the answer is yes. You didn't have to really do all that. The answer is yes. It does have a child that would be a leaf in that game tree. All right, how about these 2? All right, 2 configurations are shown. Is one a child of the other in the game tree? So remember, a child is just going to be the same configuration, but with 1 more X or 1 more O, you know, depending on whose turn it is. So look, you got the X, X, X in the same positions. You got the 2 O's up here in the same positions. But this one has an extra, you know, X and an O instead of just the O. Like, these are not the same. I can't get from one to the other one by just adding an X or an O. You know what I'm saying? I can't add an X to this to make it look like this. And I can't add an O or X to this to make it look like that. So no, these are not, one of these is not going to be a child of the other, because I can't just add a single X or a single O to make the configurations look the same. Hopefully that made sense. A configuration corresponding to a tie game is a leaf in the game, right? You know, the end of the game. What is the level of a tie configuration? Remember, you're starting here, the empty board that's level 0, right, the root. Then when there's a single letter on the board, that's level 1. When there are 2 letters on the board, right, X and O, that's level 2. So at the very end, there would be 9 letters. If it's a tie game, there'd be 9 letters on the board. 5 X's and 4 O's, or 5 O's and 4 X's. So the tie game, any tie game, will be at level 9 on the game tree. So hopefully all that made sense. Alright, so the next application, alright, apart from game trees, these prefix codes. Alright, so here, text files are stored on computers as binary strings, right, 1s and 0s, in which each character is assigned a binary code representing that character. The standard way to represent text is to have a fixed length code, right? So every code has the same length for every symbol in the file. You might have heard of ASCII. I know that stands for something like American Standard Code. I don't remember exactly. All right, I guess I could look it up, but ASCII, I've heard it said ASCII code and Unicode are examples of fixed length encodings, right? Every single symbol is encoded with a bit string, a binary string of the same length. More space-efficient codings, however, can be achieved by variable length codes. Right? Variable meaning varying. So some symbols may have a code of length 3, and other symbols may have a code of length 5 or 7. Right? It can vary. It can change. In which the number of bits for each character can vary. Right? So characters such as A and E that occur frequently are represented with fewer bits, while characters such as Z and Q that don't appear that often are represented using more bits. Trees are a convenient way to represent variable length codes for translating between text and binary. So here's an example of a variable code system represented as a tree. And you see there's the root, and each level you got 0, 1, and then a new 0 or 1, and then from here 0 or 1. And they could have also extended it this way, said here from here goes 0 or 1, but whatever. And I'll play the animation here for you. So say they're trying to encode the word mist. Right, so follow from the root down to where the character M is located, and all the leaves are the characters. All the leaves are the symbols, the letters. So you follow from the root down to a leaf, right, until that leaf is M. And look at the edges you went across. They were labeled with 1, so the code for M is 1 1 1 1 1. Simple enough. The code for I, there's I, would be going back to the root 1 0 0. Right, starting from the root, going to I 1 0 0. So I pop that on. So I got the 1 1 1 1 1 for M, and then 1 0 0 for I. All right, then for S, again, go down to where S is. That'd be 1 1 1 0. And then pop that onto the code. And then finally for T, there's T there, 1 0 1. Gets popped onto the code, and there's an encoding of the word mist based on this encoding here. Now the encodings can change. All right, this isn't the only type. I mean, this is just one example of a tree that encodes different letters, different characters, but there's infinitely many others that we could make. Oh, maybe not infinitely, but a lot. Alright, so here they have another one. Now they're asking us to decode. Right, here's a same kind of coding tree. They give it here. That is going the other way around. They give you a code, and you have to tell me what word what characters this code is encoding. So you have to decode. Right? So I'm seeing 1 here. All right, then they go to 1 again, moving down the 1, 1, 1, and then the next one's 0, and I landed a leaf. I know that the first part of this code's got to be the letter S. So let's look at the next one, 1, 0, 1. Well, let's see, 1, then 0, then 1 takes me to T. All right, so the next part of the code is T. Follow the animation. Okay, and then look at the next one. You got 0. Well, 0 just takes me straight to A, so that A has a code length of 1. Just the number 0 there. So next part of the code is A. Then this next part starts with 1, 1, 0, and the letter R. All right, so the word star was encoded by this code here. Okay. So again, you'll be going back and forth given these different variable code trees. Yeah, hopefully it's pretty simple from watching these couple animations. All right, so notice that A is encoded just using the 1-bit 0 in this example, right? Whereas Z is encoded using 6 bits, 1, 1, 1, 1, 0, 1. All right, so suppose a text message consists of 9,000 A's and 1,000 Z's. If each letter were encoded with 3 bits, the total, would be 10,000 times 3 or 30,000 bits would be needed to encode that. But using the variable length code, you only need 1 bit for each of these 9,000 A's, and then 6 for these. There's 9,000 plus 6,000 be 15,000 bits. That's half the space. Half the space would be required to encode that particular text. All right, now the code illustrated in the animation is an example of what's called a prefix code. A string S is a prefix of another string T if all the characters in string S appear at the beginning of a string T, right? Kind of like a prefix for a word. So here's an example here, right? Say S is encoded with 111 and T is encoded with 111, 101. Well, look, 111 is at the beginning of T, so S is a prefix of T. Whereas over here, R, if again, these are these aren't the actual encodings. They could be, but R is encoded 1110. T is 111101. Notice that 1110 does not begin T, so R is not a prefix of T. And these prefix codes, right? These variable coding trees that we've been seeing, the way they're constructed guarantees they're set up so that no letter's code, no character's code is a prefix of any other character's code, right? So that way you avoid confusion. Because what if I was given 111 followed by 111101? Well, then I'd go 111, hey, that's S. And then I'd go 111, hey, that's S again, when it's supposed to be T next. So having one character be a prefix of another would be a bad thing if you're trying to decode a line of code. So we want we don't want prefixes. Right? So a prefix code has the property that the code for one character cannot be a prefix of the code for another character. Right? So we don't want this to happen, because like I said, that would cause confusion when you go to decode. So the fact that the codes are organized as a tree in which characters are only stored as the leaves ensures this prefix property. Right? Because remember, in a tree, if you remember from section 14.1, to get from take any pair of vertices in a tree, there is exactly one exactly one path between those vertices. So if you set this coding up in a tree-like fashion, you'll guarantee that the code for one leaf, the code for one character, will not be a prefix for the code for another character, because they're totally different paths. Right. All right. Okay, so here's an example. All right, so here's an example of a prefix code, set up as a tree here. So use the prefix tree above to encode the letter B. So starting at the root, we're going down to B. That's just a bunch of ones, right? 4 ones. I'm hoping this is pretty simple. Right? Use the prefix tree above to encode the string. Encode the string BA. Well, we already have B as 4 ones, and then A is simply 0. Takes me to A. So 1 1 1 1 0 for BA. Use the prefix code above to encode the word bat. Well, I have BA 1 1 1 1 0, and then T is 1 0 1. 1 0 1. So I just add that on. 1 0 1. There's the word bat. All right. Now you're asked to decode. Right, and again, this is where the whole concept of the prefix code helps us. Because no character is going to be a prefix for another character, we shouldn't have any confusion decoding any binary string. 1 1 1 0. Well, I'll start with 1. All right, so 1 1 1 0. So it's just taking me straight. The whole thing's taking me to K. That's the code for K. Right. And then here you got 1 1 1 0. So that's K. Right, this first 4 bits is K. So now let's look at 1 0 0. Let's see. 1 0 doesn't take me anywhere, and then 0 again takes me to just N. So this is just KN. And then here, 1 1 1 0, that's K. 1 0 0. We saw that was N. So this is KN to start again. But now after that we have 1 1 0 1 0 1. All right, 1 1 0. See, 1 1. Now 1 1 0 is O, and that's 1 1. That takes care of the 1 1 0. And then last is 1 0 1. 1 0 1 is T, so it's not, the word not. Okay. So again, I'm hoping this is very, very simple. I feel like it is, in my opinion, it is a simple thing to do. This, especially when you're given the prefix code as the prefix tree. Now to create a prefix tree, and you could make any kind of prefix tree you wished. And if you're setting it up as a tree, you're pretty much guaranteeing that no letter, no character will be a prefix of another character. So I mean, I could jumble the symbols around, put A down here, put R here, make up your own tree. Doesn't matter, right? There's all sorts of these prefix trees. But all you're going to be asked to do is, encode and decode, right? Okay. So now you have your additional exercises. Again, if I haven't assigned them all, still look at them all. I'd still recommend looking at all the problems, just for more exposure, more practice. And you got the solutions to look at too, right? And just try to work out the problem first, though. Right? Try to work it out first on your own before you look at the solutions, right? Don't just copy solutions down and not try anything. You're not going to learn anything that way. And hopefully this video is a reasonable guide through this section. And if you have any questions, of course, send me a message. I'll get back to you as soon as possible. And thank you very much for watching.